All right, so the plan for today, we're gonna spend some time on the case study. And I don't know if you get the chance to read a little bit of what other people have done, but feel free to do so during the class as well. There's certain notes that I took down based on what people have done. But before I get to that point, probably it's easier to break out a little bit for you all to talk to your neighbors about what you have done. And I did say, so I sort of get everybody's write up here, but there are certain points or like aspects I want to address as a whole class. So maybe let me talk about something briefly before we start, and then we can break about it. So let's see.
What?
There are words for like you treat people with kindness.
Aggression.
Or
Hey, do you mind mute yourself? All right, so if you notice what people have done, there are a few aspects that I think are important to throw them out first before you break out to do small discussion with your neighbor. So one thing is, most of you are doing hierarchical model. But then exactly how the hierarchical model is done, I think has so many different flavors, okay? So one of them is the normal model. And that's directly related to what we, I think, have been doing in class. But then, of course, the normal model will have the data, the normal model is the data model, and then exactly how you're sharing the mu's and then the sigmas. I think people have different approaches. Okay? There are reasons, and it's good to see many of you writing why you want to, like, say, share the mu's in terms of a two-stage prior, or share the sigma in the same way as well, or not so much by doing some exploratory data analysis. So I think that's good. So keep in mind that's one approach we've been doing. Another one is, I guess, because I was talking about it, I added a comment yesterday morning, and then some of you start to move to this Poisson model. So this I don't think we covered example in class. Yeah, but Poisson model is typically used for dealing with, the data model is typically used for dealing with count data. So I think some of you start to do that, which is great. And I think among those of you who are dealing with the Poisson model, something interesting I want to mention now, so you can have a discussion about it, is how you are giving, so the Poisson model has this one parameter, lambda. Okay, some of you are using mu, that's fine. But typically it's lambda, so I'm going to use lambda here. And then how to put the prior, I should say hyperprior for this lambda. I see different ways of doing this. One is a conjugate one, which is gamma. Okay, so I'm just going to throw them out here. So the prior for lambda, okay? And I also saw other people dealing with normal. And actually even better, some of you are doing truncated normal, which I think makes sense because the Poisson rate should be positive. And so that was, I think, a good move in terms of what you're doing, so that's good. And lastly, I think everybody did this, is you create a new variable indicating the period of time, right? Before you're doing and after 402, because this leads to how we are going to construct the actual hierarchical model, like say among what observations we're trying to share those parameters. Okay? So I think that was also good, and I think it was partly because of the way that I wrote the question, I guess. Because when I first was doing this in the past, I didn't think about actually creating a new variable indicating the group, right, or the period. So another thing you can do, which I will share at the end, the write-up that I did, short write-up that I did, that you can simply have just different, say like observation-specific hierarchy, in the sense that I believe each of the lambda I shares, like all of the lambda i's share the same prior, which is doable as well. Okay? But I figure because of the way that I asked the question, many of you start, or maybe the first person did it, everybody else did the same. But anyway, whatever that is, I think it's good to keep in mind. And one last thing is we do have one group doing a regression, which is pretty interesting. So if you're curious about the outcome, it's the, I think it's by Houchen and Lucas. So if you see their post, you can see how they're doing the regression. We can have a small discussion about that as well. Specifically, I think, or maybe Lucas, you can talk about it, the regression that you guys did.
So yeah, I mean, like we just did a multiple linear regression for it.
And the predictor is the indicator, right?
Yeah.
Yeah, so it's, I think it's also working on this before, due, and after. You have this one extra variable, and then like comparing to, I guess, before is the reference level, and then the other ones are the non-reference level, right? Yeah, so I think that's worth checking. I mean, there's no fixed answer to how to analyze a particular data set. So most of you are doing a hierarchical model, which is great, but then even among the hierarchical models, there are so many different things you might be doing. Yeah, so I think that will be worth checking. And one more thing before we break is this gamma. So for example, if we're going to use this gamma AB as the prior for all of the lambdas, let me just use lambda I for now. And I saw some of you are putting hyper priors for it, like letting A and B to be random. So that's one thing you can do. But some of you fix them, right? Thinking that they're fixed, or you don't want that many parameters to be random in the model. So just so you know, in terms of how to specify the hyperparameter, I think that people have different ideas as well. Okay, so I think those are good things to keep in mind, and then you can explore a little bit of what other people have done. And also, I'm pretty sure you and your neighbor probably did something different, so it might be a good time to just check in to see how you did your analysis, and then maybe after 2 minutes we can talk about it together in class. Okay. And I'll walk around too, answer questions or join the discussion. All right, so my plan is I sort of wrote down what are the groups are doing, but of course we probably won't be able to get to everybody's write-up, so what we can do is I will put some stuff up. So I won't be able to share the screen now with the work now, but let's keep in mind those are the questions, and let me bring up the let's talk about maybe a hierarchical normal model first. And I'm just gonna try to see who's here so they can talk about it. So yeah. Oh, it's there. And this is the one that's easier to look at. So I'm gonna ask either Dahlia or Patrick, just talk a little bit about what you have done for the normal model. I will just scrolling the slide, the pages if you want.
Yeah, so we grouped it into like 3 time periods, like you said, like before, during, and after World War II. And we just looked at like the mean rates among the 3 time periods, and we can just like see like they're different. We plotted them, so like they just look different. So we decided to do a hierarchical model with the normal. So we assigned like each group has a different MUJ that comes from the same prior distribution.
Mm-hmm.
And we said all the sigmas are like, we set all the sigmas to be the same.
Mm-hmm.
And yeah, we gave like sigma weekly informative prior and tau the standard deviation of the views
Mm-hmm.
to gamma 1 also.
Right, so that's here, right?
Yeah, and we ran JAGs
Mm-hmm.
to get posterior draws of them. And
So if we get to the conclusion, so these are the MCMC diagnostics,
yeah,
right? Mm-hmm. And the thinning, I think you guys did one, like.
yeah.
Mm-hmm.
Our chain was like not sticky, so we didn't need to fit it
Mm-hmm.
much at all. And all the auto correlations were pretty low.
Okay. All right, and then in the end, you looked at the average of the posterior.
Right.
Wall, right? Mm-hmm.
Yeah, and they were like very different.
Mm-hmm.
So yeah, we just concluded that they were different. It was lower during
Mm-hmm.
World War II, and it was highest after.
Right, comparing, yeah, the 3 periods, right? Mm-hmm. Yeah. Sounds good. I mean, actually, like, I think, I was just curious because most of you are doing this before, doing after that extra variable. And then you are getting, like, say, in this notation, draws of mu1, mu2, and mu3. I think in addition to just looking at their means or medians, you might want to just check, say, like, if I ask the question, what's the posterior probability that the average marriage rate during the World War II is indeed, say, like, smaller than after? Yeah, then you're gonna do, I mean, you can actually report a probability instead of, I mean, I think looking at the mean summaries or median summaries are fine, but then you can also think about doing that, and we have seen that before in exercises and stuff, okay? All right, and so there's another group who did varying sigma as well, but I think none of them is here. But I do want to ask Delia and Patrick, say, what made you decide not to share, I should say, not to put the sigma also as part of the two-stage prior?
Just like in the exploratory data analysis, the standard deviations were 1, 1.03, and 0.9, so we thought they were similar enough.
Is that right? Okay. Yeah, fair enough. I mean, the other, okay, so since we're there, let me just get to, I think it's here. Yeah, we don't see any plots here, but then you can see the estimation that when, so this is from Isaac and Marin, and then they did also normal hierarchical model, but then they also let the sigma to be the two-stage prior. So you're gonna have more parameters that you're estimating here. For them, I think they have the sigma J1, 2, 3. And if we look at our their posterior means are not so far from each other, right? If you look at this column, so it's 1.026, 0.984, and then 1.067. And then the 95 or 90% posterior credible intervals are not that far away. So might be, so even if we let them to be random, or like I should say, they're all random, sorry, in both cases, but even if we let them to be shared through a hierarchical structure, we don't see much difference. Yeah, so that might be indicating that, well, in order to have fewer parameters to estimate, you might want to just keep them as random, but you don't have a particular sigma j, like what Delia and Patrick did. Okay. All right, sounds good. And yeah, I think Kevin and Hailey, you guys did a similar. Okay, sounds good. So that's for the normal model, and then let's go to the gamma Poisson a little bit. And let's see. We'll probably go to Ross and Johnson. So Johnson is not here, so Ross will have to move. Yeah.
Oh, okay. So after your hint, we kind of saw the count. You mentioned the count data, so we we originally wanted to do the normal,
Mhm.
but we just completely switched it to the Poisson, where lambda or mu,
Mhm.
and each we did the grouping on the pre, during, and post,
Mhm.
which is j is equal to 3, and for each one of those we had a mu of j.
Mhm.
So we, for this one, alpha and beta were generated randomly compared to fixing it.
Mhm.
And what we stuck with randomly generating was alpha and beta, but we were kind of weren't too sure, like kind of the fixing it, like we weren't too sure which one's the right way to go about.
Mhm. Mhm.
So this one, we randomly generated alpha and beta as opposed to fixing it.
For gamma, you mean?
Yes, and we just gave, I think, priors of A equals B equals C equals D, which is equal to 1.
Mhm.
Set all those equal to 1.
Mhm.
And turned out, well, when running the MCMC chain, it looked pretty good with the outcome.
Okay, let me
That's a little bit down
get
there,
you-
down a little bit more. We did have to do thinning, but we just, of 10,
Mhm.
that's after running it the first time, we saw that the lag
Mhm.
went up to 10. So we just put that then up to 10 and it fixed it, and it seemed it wasn't sticky and converged and had pretty low, close to 0 autocorrelation.
Yeah, so what about the results here? So this mu are the lambda that I was using, but for both of them, they're talking about the rate, I mean, the Poisson rate for the 3 different periods, right? So what do you find out from here?
I mean, it was kind of similar. It did adjust the posterior. Well, we were kind of like, we first looked at the, straight off the bat, the means for each group.
Mm-hmm.
And
Right, the means look similar to what we saw with the normal.
normal, yes,
Mhm.
that's what we
Mhm.
compared. So we kind of figured we were going in the right direction
Well,
with that one. But
Mhm.
yeah.
Yeah, so good. So I will also next go to another write-up about fixing alpha and beta. But now since we are here, okay, so the big picture here is what to give for the alpha and beta in this. So first of all, the data model is Poisson, and then we have a group effect J, right? And then each of the mean, mu or lambda, J follows a gamma, and it's shared. So now the question is how to put hyperplyar distribution for lambda, for alpha and beta, or just fix them. So let's say, so first of all, this case right now, Ross and Johnson, they're not fixing them. They let them to be random, and they give weight, I would say vague prior for alpha and beta, like both, all of this for numbers are 1. And if we go to the posterior, here, what do you see for alpha and beta? So this is the case that we think they're random, right? So, and then I'm sure you guys monitor it, so you're gonna get the outcome, I mean the posterior draws of them. So they start to look different. I mean, say we put the same gamma 1, 1 for both of them, right? They start to look different, and then what do you think this is telling us in terms of well, they're hyperparameters, so sometimes it's really hard to interpret what they are. But I would say based on the output at the moment, I feel like fixing them, if you fix them, then they're fixed numbers, so you never make inference about them. But then the posterior summary of this showing that alpha and beta are actually different, at least in the way that it's being run at the moment. Okay? But they're hyperparameters, so it's hard to interpret what they are. But if you vaguely remember what a gamma distribution is, if we go back here, for this, right? So gamma, I forgot the exact expression, but gamma, alpha, and beta, I think I mean, the values of alpha and beta sort of tells us something about those mu j, right? Like in the posterior, I think alpha is bigger, than beta, right? Yeah, I should have checked it, but I forgot, like, say, what alpha and beta means in terms of going into thinking about the means and the variances of this mu j. But I think it has some implication in terms of how variable we think those mu j's are. Okay, so again, in the normal setting, the normal model setting that we've seen before, it was easy to think about it because if you have this mu j and follow a normal distribution, the mu going to be the mean, and then that sigma, or I should say that tau, will be the variance, right? Whereas here, gamma has different parameterization, so, but then in the end, in the posterior, we actually see different values, summaries of alpha and beta. So I think it just tells us something about the variability, at least, in terms of the different mu j's. And I think that's important to see. So what we used to see, if you remember, for the normal model, is we looking at the relationship between the tau squared and the sigma squared to remember the source of variability, right? So in this case, it's doable as well. So just so you know, for the Poisson distribution, if it has a rate parameter is mu j, then the mean is mu j, and the variance is mu j as well. That's just what it is, like the distribution. Yeah, distribution feature. And then among all of the mu j's here, the rates, and whatever the hyperparameter, the summaries of alpha and beta tells us a little bit more about how we think, how different those mu j's will be, the rates will be. Yeah, for sure.
I think this parameterization, the alpha and beta are scale at beta. Alpha is like having position, and beta is scale. If I remember correctly.
Yeah, so since we're here anyway.
Yeah, sorry. Yeah, alpha shape and beta.
Yeah, so let's see. Well, I should have prepared it, I forgot, but okay. Yeah, distribution. Shape and rate?
Yeah.
Yeah, so.
Yeah. Well, I think it depends on how you parameterize it. I think the alpha beta way, because there are two ways to parameterize it.
Right,
I think
okay.
the way we're doing it assumes the shape and scale.
Yeah, I see what you mean. So just to double check. How does JAGS do it? So you see the gamma that the JAGS is doing it is R and lambda. So this looks like shape and rate, I think. Right? Let's see. You all should look at it. I might make a mistake here. So this is the density that they have for this gamma. So I think it looks exactly what we usually do with the parameterization. So my guess is the alpha and beta that we just used in JAGS is the shape and the rate here. If we follow that, you can see that the mean is alpha over beta, right? And then the variance is alpha over beta squared. So that's the stuff that I was trying to say, that a priori, when you put the prior, that you let them to be random. And then, of course, in the end, in the posterior summary, the relationship between the alpha and beta, the scale of them, and then, of course, the computation of the mean and the variance, you can say something about how variable you think those mu j's are.
Right.
Okay? Less intuitive in the, comparing to the normal model, it's less intuitive, but it's still something doable.
Well, I guess like a rate is just like an inverse of a scale, then, right? I think that's the traditional.
Yeah, that's right. Yeah. So between these two, I think one is the inverse of the other one. Okay. All right. Sounds good. So if we go, so that's the thing I was trying to say here. This, the posterior draws and then the values of the alpha and beta sort of tells us something about, in the posterior, how variable we think across the three different periods, the rates are changing, right? You can look at them, of course, in terms of the posterior summary. So you see here. So just now we're looking at the median or the mean or the 90% confidence interval, right, for the mu j's. But you can see that there's also, well, it's hard. Again, it's harder to look at these standard deviation because it's not really telling us about comparing to the mu j's, right? So those standard deviation, this column is looking at the deviation across within each of the MuJ. Okay? But what I was trying to say about understanding alpha and beta is sort of telling us across the different MuJs how different they are, because that's being captured in the hierarchical model. And so if, say, one of the research questions is exactly about it, then you'll be able to give some evidence or give some conclusion based on the values of alpha and beta in their posterior draw. Okay. All right, sounds good. So one last thing, I guess, in the same setting here is how to, yeah, I didn't notice, so I think Ryan Elliott. Well, since we discussed all of this, I don't know if there's some extra reasoning of why you guys fix alpha and beta. There's it. No, that's it. Further down?
Mhm.
Oh, okay. Yeah. Any comments on this? No? Okay. I guess it was just easy, so you set them to be fixed. Okay, yeah. But I mean, sometimes this set in particular, I think is a small data set. Yeah, so sometimes people might want to reduce the number of parameters that you have. Yeah, so might not be a bad thing to do, but then the assumption here will be that you are thinking that the mean, yeah, in fact, the mean and variance for the MuJs are both 1 in the parameterization that we see, right? Because it's 1 over, like alpha over beta, and then alpha over beta squared. So for both of cases, it's 1, which is not bad, yeah. But it might be good to keep them random. Okay. So that's why. That's why. Okay. So you see, you guys did track the mu, but because it's fixed, so we'll never get anything. And I think that's why the NA is. Okay. Yeah. All right. So I think that's all for. Oh no, one more thing. I think Gabe and Herrick talked about how to. I think you guys did a truncated hyperprior, which I would like to. So, any of you wants to talk about it really quick? Is the prior that you guys give is different from most of the others? We want to see how you thought about them and how the results are.
Yeah. So we did a similar thing to the other group that used the Poisson distribution, but the difference is that for alpha and beta, for the prior distribution on the MuJs, we used a truncated normal instead of 2 more gammas. And my thought with that was just that, like I figured that like the alpha and beta for the gamma would be like I wanted to have like sort of a symmetric shape for the sampling for those 2 parameters, where like gamma wouldn't give us that, but a truncated normal would give us like something more close to that.
Good point. So gamma is definitely right skewed, right?
Yeah.
And then normal itself is, if majority of that normal density is positive or negative, then it's going to be definitely more symmetric than the other one. So let's see how the results are. Yeah, so the A and B here, well, I think overall the MuJs, I think all of us get similar results, which is not surprising.
Yeah.
And then the AB here, so it looks like the prior does play a role.
Yeah, I think I was comparing numbers when we were looking at the other.
Oh yeah. So what did you find out?
I think we have similar betas, but our alpha is maybe like 1 less.
Yeah, smaller, right? Smaller than the other ones. Yeah. So I think this again is so it's the same data. I think overall the same model as well. So I guess this is actually a good example, as you can see how the different prior. Well, we'll be again. I think because we don't have a lot of data points, so that's why the prior you start to see that plays a role here. And using 2 types of prior do give us, in this case, different values in the posterior for A or alpha in that notation. So I think it's well, I mean, there's no which one is better or which one is worse, but it's more about in practice, there are cases that you might want to try out different priors just to see how things play out. And sometimes, yes, if you have, so all of this are sort of weakly informative prior, I think. But then sometimes if you do have strong opinion about certain things, then those can be factored into the prior, can help you a lot in terms of the. Okay. All right, good. So what else? I think most of them. Oh, there's one. Okay, there are two other groups that are doing interesting stuff. It's still hierarchical Poisson, right? Yeah, hierarchical Poisson, but then the prior is altogether different. So let me. Those four here. So Major Ryan. So let me share that, and then anybody wants to talk about it, Nate or Brian, whoever.
Yeah.
Uh-huh.
Similar to what Henrik and Gabe did, we did each separate group from the Poisson, and then we also used the truncated normal. We didn't think marriage rates should be below 0, so we truncated at 0, and then for the hyperpriors, we did the same thing and left mu with the truncated normal, and then tau came from the gamma.
Yes, the difference here, even though it's all truncated normal, the difference here is that you guys are putting a normal prior distribution for the mu j, right? Instead of the conjugate gamma.
Yeah.
Yeah, and I guess the reason why you want to truncate here is because you want to have positive rates. Okay. So yeah, and then right down here for the hyper priors, you can do that as well. So let's see. So you guys doing thinning of 50? So was it really sticky earlier?
It was, but I think I actually might have made a mistake on that because I was looking at like the tau and sigma, and we don't actually use sigma. So I was trying to eliminate the stickiness there, and that wasn't actually in the model. So that was a slight mistake.
I see. So those are extra.
Yeah, exactly.
Like, okay, makes sense because it's only mu and inverse tau.
Exactly.
Okay.
Exactly.
Oh, because this, I guess, was from previous stuff that we used to have the data model to be normal. Yeah. Okay. Fair enough. So I guess, yeah, but I mean, doing thinning doesn't hurt. It will just even improve more of what that is. So let's see. So all of the mu j. So this time I think mu j1 and mu j3 seem to be slightly lower. I mean, everything seems to be slightly lower than the other models that we fit. And so what is sigma? Oh, sigma.
Sigma shouldn't be there.
But it was wrong. Okay. So what's mu again? The mu and tau, they're the prior, hyperprior.
And then each of them uses the separate groups for before doing that.
I see. Okay. I see. Okay. All right. Sounds good. So before we go, I think Tyler and Jim also did something similar. Is that right?
Yeah, I think so.
Here. So maybe I will just go to the model part really quick.
Yeah. Right, so we also truncated, but what we did was for our Poisson model of the likelihood, we used the probability. So we had 1,000 times, and we just kind of went 3 decimal places backwards to show more of a probability per 1,000 people. So we also used truncated, normal 4p, and actually, if you look at the prior from J from 1 to J,
here?
So our PJ actually, or our P actually models for the average sum of means per group. So if you look down at the summary for P is about 28, and actually that model did not converge when we did MCMC diagnostics because P is actually modeling for like before World War II marriage rates over those 4 years, and then it like per group. Does that make sense?
Not yet. Sorry.
Okay. Yeah.
So this P, you're saying that this extra parameter.
Yeah.
Okay. So let's.
So go back. Yeah.
yeah, in the model.
Yeah, so
Oh,
if you
down
look,
here.
right, if you look above at the likelihood, we
Uh-huh.
have PJ, and then inside of PJ, and the
Oh,
percent
that's
model.
the mean.
So yeah, but go up one more at the YIs.
Uh-huh.
Yeah, right there. So we have PJ, and then inside of that, we have the years
Mhm.
iteratively.
Mhm.
So that's step by step, but then the actual P that models for PJ
Mhm.
is the total sum of the means in each group.
I see.
Yeah.
But then the total number of observations are still capital N.
Yeah.
Okay. And then this year's is.
So
what-
years goes in and looks at class before,
A
during, and
period.
after.
I see. I see. So it's not literally like years. It's,
Yeah.
Okay. Okay. So it's still the periods that the other groups are doing.
Yes.
So this is like 3 different groups there.
Right, exactly.
Okay.
Uh-huh.
But then, because you're working with probability and then trying to, then the interpretation of the actual P will be different.
Right.
Okay.
So actually, it still comes out, well, we have convergence for our 3 groups.
Right.
And we actually, just another thing that we noted was we included 1939 as pre-World War, and we included 45 as as
Okay.
during World War,
Right. Right.
which definitely affected the numbers, but I think our conclusion was the same as everyone's.
Okay. Sounds good. Yeah, I guess we never, yeah, all of us, I mean, I didn't get to even talk about how you guys create that one extra variable, right? I mean, it's the before, during, and after, well, there are those particular years, like 1939 or 1945,
yeah.
how you want to define it.
Right.
Yeah. Okay. Yeah, but it's all marriage rates in Italy, right? So I guess, yeah, I mean, focus on the country of Italy itself probably would be the best way to do it. In terms of like
In terms of
when it
involvement.
started, yeah,
Right,
involvement and when it started,
Right.
and when, yeah. All right, sounds good. And I think one last thing, just want to show you all what the regression group did, which is pretty interesting. Get it out here. And I think I'll just supposed to say something about it.
Yeah, so we just, so we have our reference group to be the before World War II group, and then we have during and after. And then we have the equations for the mu-i's for those specific groups there, and then we assume independence of the betas, and we assume normal distributions for it, and then we plug it into JAGs.
So can you tell a little bit more about what the I mean, say the model itself?
Oh, so we're just assuming a linear relationship for.
So mu-i is what? Mu-i is the average
Exactly.
of the rate.
Yeah.
Okay, for each
Group.
year.
Yeah.
And then you have, so I guess those xi1 and xi2, they are the dummy, or like variable, indicator variable, right?
Exactly.
So yeah, so that's why, so this is the example of you're running a simple linear regression, and then your predictor is a categorical variable, like in this case with 3 levels. So that's why your mu is going to be beta 0 if it's talking about before World War II, beta 0 plus beta 1 if it's doing, and then beta 0 plus beta 2 if it's after. So then the interpretation is going to be quite different, just because of the way that the model is set up. So I guess diagnostics wise, everything is fine.
Everything looks diagnostics.
And yeah, you don't even need to do much training. Good, and then yeah, all right. Yeah, so in terms of, I guess, to really compare, say like, do things change? Like before, during, after, I guess people can then work on looking at the posterior summary of beta 1 and beta 2 instead of, like, say, the mu's or the lambdas that we have seen in the other models, because now this is talking about change from the reference group. So let's maybe take a look at beta 1 and beta 2 real quick. So beta 1 is comparing
during and before,
and it's strictly negative, right? Okay, so that means a drop. And then beta 2?
That is before and after.
So, well, the median is positive, and then you see some kind of, I mean, I don't know, like 30% of them maybe are below 0, right? So comparing to this group is less, it's like, I guess, not as big differences we saw. And then I think that's in line as what we saw in the other output of the models that we have seen. Okay. All right, cool. So that's all that I want to do for the discussion. I will post whatever I wrote on Moodle as well. But before we go to the before we use the remaining time to do the Q&A for the project, there's a couple of stuff that I prepared for just showing you some other hierarchical models that you might be able to do. So I'm just gonna, we have seen these gamma Poisson, or at least the Poisson likelihood, or like the Poisson model. So in this marriage rates example, so here is, yeah. So on the left is what I was talking about that I did, that I wasn't even breaking the different periods, and then I'm just treating each of the year as I ID from the same gamma prior. So that's why you see in the prior section, I have lambda. I mean the loop goes from 1 to capital N, and then they're all sharing the same. So it's a different ways of sharing. I think they're good and bad in both. I was guessing most of you were doing approach 2, which is an array that you create this J in the priors in that index because you saw the question was talking about before, during, and after. So you can certainly do that. But if you think they're all sort of independent and I want to learn about them overall, then you can set whatever that is written in approach 1. But then I realized it's actually pretty hard to summarize the output from the approach 1, especially if you still want to answer the question about changes between, like from, as you say, before, during, and after. Because now you have, is it 11 years in total? I forgot. 11 years? Yeah. 11 years in total, so you're going to have 11 different lambda. And then they're still like coming from different periods of time if you define them. So yeah, I think it's getting harder if you do that. So just so you know, you can do it, but then it really depends on the research question that you have, and then how you want to structure your hierarchical model can be different. And I think this links to what we talked about when we were looking at Josh's model, right? When we're doing, like I was saying, that there are so many different ways that you'll be able to share those parameters, and how exactly you want to do it depends on the context, depends on your belief, depends on whatever was done before. So I think this is another example. But since everybody's doing approach 2, so I guess it's still contrast here. But I will upload whatever I did, and then you can take a look at the results. But based on my observation, I think it's harder to summarize the approach that I did, just because they're all broken into each year separately. All right, so another thing, I mean, we've been learning about this beta binomial conjugate as well, or I should say if your output is like say number of successes out of the total number of trials that you do, then it's pretty natural to develop hierarchical beta binomial model as well. So this is a data set, say it's the number of heart attack cases, the number of resulted deaths, and then the percent of resulted deaths of 13 hospitals in New York City in 2015. So you can see that the cases, so there are 13 hospitals here, and then the cases, the column of cases, the total number of heart attacks in that hospital in that year, okay? And then we're interested in the death rate. Okay? So then, well, so the cases are the total number of, cases here for each hospital, and then the death will be, if you define death as a success, then this are binomial data model will be suitable, right? And then for that P, which is the success probability, then putting a beta as a conjugate, and it's going to be between 0 and 1, so it will be a natural choice over there. So, so for example, you can do, so there are 13 hospitals in total. Note that each of the NI is different as well. So if you try to write the likelihood, you're going to have YI, binomial NI, PI. And then I'm sharing 2 state prior for all of the PI here. Okay, so that's equation 2. And the beta, AB, well, whether we want to fix them or whether we want to further give hyperprior hyperplayar distributions. It's up to you how you're going to do it. And one graphical representation that you can do will be like this. So A and B together contribute to each of the PI, right? And then PI together with the NI like affect this YI, which is the outcome. And yeah, so that's all I want to talk about in terms of the case study 1, as well as any additional material for the hierarchical models. I posted this already on our Moodle, so if you want to take a look, feel free. And then the rest of the time is going to be used for in-class Q&A for your projects, and I brought those papers along with me just in case we need to look at them. But yeah, so you can start, I mean, if you want to move chairs a little bit, just sit with your teammates for your project, feel free to do so. There's some space like behind the last row